My presentation will be about how we utilized supercomputer in the shipbuilding industry. And I will talk about three things today. And the first one is what we've done in the K and post-K priority issue, and also in the K industry used. And last one, I will talk about commercial use in this new technology. And in this slide, I would like to talk about our target. And in the business negotiation, a ship designer defines the main dimensions such as length and draft and breadth and depth and weight and speed. And they roughly estimate the necessary power from their database, and they calculate up to 100 types of ships by CFD. So we can say that CFD is widely used as a numerical model basin, but utilized in only an early stage. And at last, they confirm the power from the towing time test, and our main target is here, replacing this by a high-fidelity CFD using direct turbulence simulation. And this is a towing time test, and we are using 400-meter long towing tank and 6-meter long model ship. And in 2011, we launched a mini joint project with 3 different kind of specialists, Professor Kato of University of Tokyo and Mr. Yamade, and myself, in order to develop a code for ship flow simulation by adding a new function to the existing code. And the K and post-K priority issue number 8 is used this part. And so as to follow after, we started validation with more practical ship with 8 shipyards. And the computer resource of K industry use is in this part. And now I will introduce about what we've done in the priority issue in the past 8 years. And the computational code we've been using is called Front Flow Blue, which is originally developed by Professor Kato, and it is an incompressible large eddy simulation solver, and it has function of dynamic overset and ALE and rigid motion of 6 degrees of freedom, and VOF function is implemented in this project, and it has grid refiner, which can refer the original CAD data in the solver automatically and tune that for the massive parallel computation. The first computational model was KVSCC2, which is a famous marine CFD benchmark ship. The computational grid is composed of all hexahedral cells, and the initial mesh is designed in order to resolve the target boundary layer, refining 3 times. And the maximum number of the grid became 32 billions by the refinement. And the first computational result shown here is a VORTEX structure at the MIDSHIP. And this is a zoom-up movie of the velocity vectors. The result, this result was the first world first computation with the whole result LES around the ship. And as a result of computation, the total resistance is compared between our experiment and simulation. The green marks indicate our experiment, and the red line indicate the correlation line, and the blue marks is a computational result. And as you can see, the initial mesh underestimate the experiment, but for the higher Reynolds number refined 3 result are they, they predicted well with a very high accuracy. And in 2017, we finally succeeded the implementation of VORTEX function in order to simulate the free surface around the ship and also confirm that the estimated wave-making resistance had enough accuracy. This is also the world's first simulation which saw the free surface and the turbulence boundary layer directly at the same time. And last year, we finally reached to the self-propulsion simulation. We can see that these propeller, the vortex from the propeller hit the rudder clearly, and this movie is colored contours. Contours indicate the hull surface pressure, and black and white shows the streamwise velocity distribution. And now we can see this complicated phenomenon around the propeller very clearly. And here, I think the most important thing is that we can use this information in the actual design scene, which is impossible by the experiment. And in order to predict the necessary power of the actual ship, we have to obtain self-propulsion factors, and we confirm that those values are estimated with very enough accuracy. And during this research, some media reported our achievement in 2014, the Nikkei newspaper, and the next year, Nikkan Kogyo newspaper. And in the same year, we won the Best Paper Award at the international conference. And this is Keisan Hyakkei, which is a public relation magazine of RIST. And the story so far was about the development of simulation 2. And at this point, we only have one validated data. So in order to obtain more reliability, we started the validation with 5 different practical ships by using the computer resource of K industry use with a consortium of 8 shipyards. And this figure shows the difference between simulation and the towing time test. And for KVLCC2, this figure is already shown before, and these bars are calculated from this figure, the difference between red line and the blue marks. And the other result, A, B, and C, D, E, shows the same trends as KVLCC2, which means initial mass, the red bar, underestimate the experiment, but for the refined mesh, orange and the yellow bar estimate the experiment with high accuracy. But in case C, you can see that the result of all resolution was underestimated. And the reason for this is that the turbine stimulator didn't work properly in this simulation, and it remains as a future work. But from the other side of view, very important information was obtained, and I think it will be very useful for the actual towing time experiment. At last, let me introduce some interesting results from CFD workshop. And this is used, also used the computer resource of K industry use. And CFD workshop has almost 4-decade history and will be held every 5 years. And in 2015, they adopted a new benchmark ship called Japan Bow Carrier to investigate energy-saving device effect, which has been a hot topic recently. And the wake distribution were collected all at once from many organizations in the world. And very interesting is that almost of all results were poorly predicted. And the previous benchmark ship KVSCC-2 has been used almost 2 decades. And they reached to the best turbulence model and settings, but we realized that it was hard to simulate a new ship. This one is experiment and the other one is simulation. And the point is they can estimate the hooks here. And this one is from Europe, and UK and Germany couldn't predict it well. And the French also didn't by using the local refined grid. And Japanese results were also underestimated. And these are from the rest of Asia. And I thought the two results were better than the others. And one is from Philippines and one is from Korea. And I asked the Korean researcher, and he said that he tried about 20 turbulence models and picked up the best one. This means that their method never can be an alternative tool for the experiment. And we could reproduce the wake distribution without any care or tuning. And now we're working on the practical realization. Our organization, SRC, has a long history of commercial tank tests, so we can use the same business framework. And important thing here is a third-party standpoint. And we started the market research last year, but reality was not so simple. At first, every customer is surprised and they express the greatest compliment. But when it comes to price, they believe that the CFD is cheaper than the towing tank test. And now we are trying to convince them the fair price, including the cost for the computer resource. And at the same time, we found that the validation data was not enough for convincing them yet, because, for example, the other loading condition is not validated yet, but they have to optimize with all kind of loading condition totally, and we have only few experience of energy-saving device which has been competitive in the shipbuilding market recently. So we have to continue to increase more validation data. And another issue came up was about the model scale. In 2012, the cost for one ship simulation was estimated as 1 billion yen. And now we can provide a service for 7 million yen, which is the same price as a towing tank test. But only a half Reynolds number simulation is providable when we think it as a commercial service. And unfortunately, our customers misunderstand that the closer from the model size to the actual size, the more accurate prediction is possible. But the difference between 4 meters here and 6 meters is much smaller than this distance from 6 meters to 300 meters. They mix up the experimental errors such as model manufacturing error and the larger disturbance compared to the smaller measurement force for the smaller model, and which simulation doesn't have any of them. So in order to remove their misunderstanding, we proved that the 4 meter simulation can accurately extrapolate to the 6 meter result. On the other hand, there is a choice to wait until 2024, when the full model scale simulation will be affordable. And there's also pure research issues with the post-K written here. And of course, I think higher resolution numbers simulation will be in the scope, and more issue in the actual C will be reliable in the post-K era. And I will talk about detail in the next panel discussion. And now I will finish my presentation. Thank you very much for your kind attention.